Oh wait, I think, hold on, let me double check to make sure I uploaded those bullet points. I realize, oh yeah, I did, they did, okay. Yeah, it's there. Can you hear me? Is my sound working? Okay, good. It was like, no one's answering, I'm worried. Cool. Oh, no wonder it's hot. My window is still open. Be right back. Cool. Everyone have a good weekend? Anyone have a good weekend?
It was okay.
Well, next weekend is a long weekend, so even if it isn't for some classes, it is for us. So I guess I'll talk more about that in a minute when we officially start. All right, so it's 2, so let's get started. Welcome back. Again, I hope at least some of you had a marginally okay weekend. It was a very unenthusiastic response, so hopefully things will go better after this. But yeah, so we are going to get started talking about volcanoes today. And so this is already the last topic before our next test. So I figured it would be better to have more smaller tests than to have you learn a whole bunch of stuff for a very few number of tests. So our next test is already coming up next Wednesday, which is the 14th. And so as a heads up, so the stuff on today's lecture and Wednesday's lecture are the last content before that test. Then Monday, we do not have class on Monday. So I know that the state doesn't give you Indigenous Peoples Day. I don't know if they ever did, but I'm going to give you that because we otherwise don't have any holidays in October. So we're not going to have class on Monday, but that'll be sort of your day to prep and sort of get ready for the test, which is on Wednesday the 14th. And so that test is going to cover basic rock types and the rock cycle. It's going to cover igneous rocks, and it's going to cover the volcanoes stuff from this week. So that is it. So there will be another quick quiz that's up today right after class. And then there will be one more of those after next class. But other than that, just don't forget to do the practice problems for the liquidus solidus stuff, because again, you will have some questions about that on the test. And I will give you that chart. So again, you don't have to memorize that, but be familiar with how to use it. So that's just kind of how things are looking for the next 2 weeks. Can I post more of those, please? What do you mean those?
Of the practice problems?
Okay. I guess I can come up with some more optional ones. Yeah, I guess I can do some more for that. But another thing you can do to practice is also just go, okay, I'm going to come up with the temperature and pressure. and see where it goes. But yeah, I can definitely make some more optional practice problems that won't be worth points, so you don't have to do them. Any other like logistics-based questions? And if you were someone who had trouble getting Lockdown Browser to work last time, I mean, I think pretty much everyone actually took the test, so we were in good shape. But if you were having trouble, I know I'll reach out to, there were a few of you who I was emailing with a lot, but if you were having trouble, we should figure that out before the 14th. So it's not a panicked issue to make sure that's working. And that fake test is still open. So if you want to, test a new browser or test a new machine or whatever, that's still there from last time, so you can practice using it. And oh yeah, I have office hours tomorrow and next Tuesday. So you have 2 more chances to come to office hours before the next test. But today, well, I guess, does anyone have any more questions in general, or should I get into volcanoes? All right, so let's talk about volcanoes. This chart is not a real chart. This is an XKCD comic. This top row are all real kinds of volcanoes, but then these are fake. So there isn't, is this test our midterm? We don't really have a midterm in this class. There are just these 4 regular tests. They're all the same. They're all, the 30 question multiple choice tests. There isn't like the midterm, but there is the final, which we'll talk more about later. Yeah. But yeah, these 4 are real. We'll talk more about different kinds of volcanoes on Wednesday. But today we're just going to talk about what are volcanoes and how do they work and where do they show up and what do they do in theory. There we go. So a volcano, I mean, I feel like that's one of those things that like we can all sort of picture what a volcano looks like, right? Like when I say volcano, how many of you picture like a pointy mountain spewing fire? Like that's your very common, I see a raised hand. Yeah, it's a pretty common conception of what a volcano is. Yeah, and it's okay because that's sort of your archetypal volcano. And actually, next time we'll talk more about Shark Boy and Lava Girl. Oh, I saw that, but a long time ago. Volcanoes are something that movies tend to get very wrong, but we don't have a whole lot of time to get into that. Well, maybe more next time. But yeah, most of the time when you think of a volcano, you think of a very pointy mountain spitting out fire. And honestly, that's not terribly wrong, although it's not actually fire, it's actually liquid rock. JoJo Part 2, I haven't seen any JoJo. I know it's terrible that I haven't. Yeah, there's a lot of, I mean, volcanoes are a very popular thing to put in fiction because who doesn't want to see a cool mountain shooting fire, right? Except it's liquid rock, it's not fire. But yeah, and actually a lot of them do end up extremely pointy because of the fact that they're spewing this stuff out and it's piling up very symmetrically. So if you see a very pointy, very symmetrical volcano, that means it's a very active volcano. But we'll talk a lot more about that next time. I can't believe there's a JoJo conversation happening. But anyway, I guess I'll have to watch that. But yeah, a volcano. There's 2 definitions, sort of 2 ways to think of it, but they're related. So one is just it's a vent from which melt from inside the earth spews out onto the planet's surface. So basically that just says there's an opening and melted rock is coming out. And then the second definition is that it's a mountain formed by the accumulation of extrusive igneous rock. And so the reason these are kind of 2 parts to the same definition is that not all volcanoes form mountains. I mean, most of them do, and especially all of the ones that you're going to see in fiction are going to be mountains. But like a mid-ocean ridge, if you remember, a divergent boundary between 2 oceanic plates, that's just the plates are pulling apart and oozing stuff out. It doesn't really form a mountain, but it is still a volcano. It is still a vent. And there are some other kinds of volcanoes that actually form indentations rather than mountains because of the way they blow up. But we'll talk more about those on Wednesday as well. But yeah, when I say volcano, I mean the vent thing. So yeah, Yellowstone is exactly what I was talking about when I mentioned that some volcanoes form an indentation rather than a mountain. So for those of you who don't know, although I guess fiction loves this one, Yellowstone is a very, 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 very large volcano. It is kind of volcano called a caldera, and we'll talk about that on Wednesday. But yeah, for the most part, though, they form mountains. But this definition that says it's a vent for molten rock is kind of the more broad general thing that allows these things to make different shapes, even though like 95% of the time they're mountains. But they tend to go hand in hand. But any questions about this definition? By the way, the lightning in this picture is just because there is electric charge happening in this hot rock. Sometimes, especially if it's very metal rich, you'll get electrical charge. And so this lightning is actually caused by the volcano. But yeah. So basically these things form where rock melts and rises. So in order to get a vent through which molten rock from inside the earth is coming out of the earth, you need to have that rock rising up. And so what I brought back here is those pictures from when we talked about how rock melts to begin with, from when we talked about how igneous rock forms in general. And so hopefully these look a little familiar, because basically every place where you get rock rising, where you get molten rock rising, you get volcanoes. So in those cases where you have a mantle plume, again, where it's that like superheated kind of flamethrower shooting up from sort of the mantle, the boundary between the mantle and the outer core. In that case, those don't care about plate boundaries. Those just happen where there happens to be a lot of heat. And so that just is going to blow torch its way through whatever kind of plate is above it. And so in that case, you can actually get what's called a hot spot volcano, which is just directly above one of those superheated plumes. Might be, it's usually in the middle of a plate, like in Hawaii. Although in some cases, like Iceland, it is, they happen to line up with a plate boundary. But actually Yellowstone is another example of something like this. It's just that it's happening on a continent rather than in the ocean. But it's the same idea of this superheated plume just blasting its way through the crust. And so that's decompression melting, but it's also heat transfer melting because, hot stuff melts stuff next to it. So, and do you all remember how decompression melting works, basically? So that idea that the pressure inside the earth allows rock to stay solid even if it's really, really hot. But if rock of that temperature then rises to somewhere that's less pressure, it'll melt and then keep rising and keep rising. So you get that with a plume. You get that beneath a continental rift because that's basically by stretching the continent, it's decreasing the pressure. It's allowing this hot stuff to rise up and just leak out of these cracks that come from stretching the continental crust. So you get volcanoes in rift zones. You get volcanoes where continents are trying to split in half. So like Mount Kilimanjaro in Africa, which is at the beginning of The Lion King, for example. But you probably also, it's very famous. You've probably seen photos of it without necessarily knowing its name. But that's an example of a rift volcano where decompression melting from Africa trying to tear itself in half is causing these volcanoes. You also get volcanoes at mid-ocean ridges simply because that's a gap. It's the place between the plates that's just letting the lava leak out. And so it's just this stuff as it rises into the space between the plates, it decompresses because it's rising and it just spills out. So you get volcanoes at subduction zones because this is a case where it's actually more about flux melting, where it's related to volatiles, where the downgoing oceanic plate pulls water into the lower crust and upper mantle, and that helps it melt and then rise to form either a volcanic arc on land or an island arc in the ocean. And so all of these things, hotspots, continental rifts, mid-ocean ridges, subduction zones, are places where you can get volcanoes. And so, most of these are plate boundaries. Hotspots are wherever they want to be. But you don't get volcanoes at continent versus continent convergent boundaries, because you don't. That's again like two giant trucks crashing into each other, and just everything kind of squishes up. And so nothing is being released. Pressure is being increased. No gaps are forming. There's no volatiles involved, so there's nothing that causes melting. And then similarly at transform boundaries, where plates are just sliding side by side, again, they're sliding side by side. The amount of pressure isn't changing. Nothing is going up, nothing is going down. There's no volatiles being introduced, so they just slide, no volcanoes. So here in Southern California, on our transform boundary that is the San Andreas Fault, that's why we're not gonna get volcanoes. So that movie Volcano, where they have Mount Wilshire erupt out of the La Brea tar pits, I mean, there are a lot of things wrong with that, including the fact that the La Brea tar pits is a sedimentary environment, but that can't happen. That very much cannot happen. Volcanoes in LA cannot happen. But are there any questions about how different kinds of melting in different kinds of tectonic settings affects why volcanoes do or don't form there? Yeah, there's kind of a lot of stuff on this slide. So we're all clear on this? Okay. So you've got molten rock, and it's rising partly because of decompression and partly because heat rises. And when it burns through the crust and pours out, then it's a volcano. And so again, to make sure to get the semantics right, so long as that liquid rock is still inside the earth, it's called magma. And then as soon as it erupts onto the surface, it's called lava. So the fact that if we go back to our silly first slide, whoops. The reason it's calling this the pedant's bane is because it has the lava inside and the magma outside, because if I see things like that, it makes me mad. So yeah, magma's inside, lava's outside. Cool. So even though there's a lot of different kinds of volcanoes, and we're going to get, again, next class is going to be pretty much about the different kinds of volcanoes. They still have a lot of very common features. And actually, even if they, except for mid-ocean ridges, which are really just like a gap. And calderas, even calderas, which are an indentation rather than a mountain, still have features like this. It's just kind of inverted. But all volcanoes kind of have this basic setup, where you have the magma chamber, which is kind of its reservoir, its source of molten material. And so that's what exists inside the crust, under the surface of the earth. But that's where a lot of the melting and decompression is happening. So all of the stuff that rises up and out, from there is what eventually forms the rest of the volcano. And so that pipe that's coming out of the magma chamber is called the conduit. Some people actually also just call it the volcanic pipe. Like, if you call it a volcanic pipe, that's fine with me. But conduit is a term people use more. And then the spot where it comes out of the top of the volcano is, or of anywhere, is called a vent. So a vent is just like how an air vent, like my air conditioner is going full force right now, an air vent releases air out of the pipes. A volcanic vent releases lava out of the pipes. And so the second it exits the vent, it is lava, not magma. So you can have a vent at the top, and usually at the top, you're going to have what's called a crater, which is like an indentation that's usually caused by explosions blasting out some sort of an indentation, or sometimes by things collapsing to make an indentation if the lava has gotten out of the way and suddenly there's a hole and the solid rock falls into it. So actually a caldera, again, is sort of the whole thing is a crater rather than a mountain. But yeah, the crater will be an indentation at the top that usually has the main vent in it. But sometimes you have vents on the side, and they're called side vents. A lot of these names are very literal. a conduit or a pipe, a chamber or a reservoir, a vent. Then if you have enough lava comes out of the vent and spills over the crater, it's going to pour down the side of the mountain and make a lava flow. And so most of the time when you think about a volcano, you think about kind of like what's happening in my background picture, where a lot of stuff is fountaining out of the sides and then flowing down. And so for the most part, volcanoes are made of just piled up lava flows, and sometimes piled up other stuff. Again, we'll talk more about that on Wednesday. But the reason that you get this cone is because the lava comes out the top and pours down the sides, and it wants to flow downhill, like everything wants to flow downhill. And so more of it is going to exist at the bottom than at the top. So does that make sense? So some other stuff, if you remember when we were talking about intrusive igneous rocks last time, we talked about dikes and sills. Whoops. So a dike is going to be like a sort of a flat pipe inside the volcano, and a sill is going to be a more horizontal. This one is weirdly not horizontal, but they're usually more horizontal, just pools of molten rock that are still inside the volcano. Or often they'll be in this area of the crust near the magma chamber. And then depending on the kind of volcano, some of them make a lot of ash, some of them don't. And we'll talk more about why in a minute. But again, this basic diagram is going to be true of pretty much all volcanoes. On Wednesday, we'll go into more details of specific kinds. But does this make sense for now? Any questions on this for now? And if you find yourself confused about this by the end of the day, don't worry, we'll see more later. But yeah, so this is your basic volcano. So different kinds of volcanoes behave in different ways. And so all of them erupt molten rock. Lava comes out of every kind of volcano. Like, that's part of the definition. If it's not letting out lava, then it's not a volcano. Now, I mean, they're not necessarily erupting literally all of the time. In fact, most volcanoes are not erupting most of the time. But they have to be capable of doing that. And so by definition, a volcano has to release molten rock. But the way in which it does it really depends on a lot of factors. Some volcanoes just leak and other volcanoes explode. And so when we talk about sort of oozing versus exploding, we call that the eruptive style of the volcano. And so there's kind of two end members. There's two main kinds of eruptive style. And in general, every volcano is going to have one that it does most of the time, but it might occasionally do one of the others, depending on the conditions of the time. But basically, the two major kinds of eruptive style are called an effusive eruption and an explosive eruption. So effusive is oozing. Basically, an effusive eruption is going to be a slow, long-term release of lava. It's stuff just pouring out of the volcano. It isn't even necessarily shooting out. It's just kind of oozing. And usually it moves pretty slowly. Usually this happens over a pretty long time, because even if there's a whole lot of stuff in there, even if the magma chamber is really big, just because it's moving slower and not exploding, it's going to spill out at a slower, steadier rate. And so effusive eruptions can go on for decades. So Kilauea in Hawaii, which the name Kilauea, by the way, literally means spewing in Hawaiian, is an effusive volcano. And it erupted from 1983 to 2018, one continuous release of lava and or gas. So that's a slow eruption. I mean, that was a pretty extreme one. I think that's actually the longest continuous volcanic eruption on the record. But it was slow. I mean, the longest one on like history. There's evidence in the geologic distant past of things that lasted longer. But yeah, effusive, slow oozing. Meanwhile, explosive is just exactly what it sounds like. I mean, there's, it's an explosion. Basically, rather than oozing, the volcano will blow up like a bottle popping a cork. Like, there's just so much pressure inside that, then rather than just spilling, the whole thing explodes. Sometimes the explosion is just that whatever is in the conduit, whatever is in the magma, in the pipe, gets blasted out of the way, kind of like clearing a clog from your drain. except hopefully your drain isn't going to explode ever. But sometimes, if it's really extreme, the entire freaking mountain will blow up. And again, that's more of a topic for Wednesday. But yeah, these are sort of opposite ends of the spectrum: effusive versus explosive, and that is eruptive style. So any questions about that? Yeah, if explosive eruptions usually take a lot less time. Like usually there might be a series of explosions, but like usually once it has blown up, once the cork has been released from the bottle, like think about your New Year's Day champagne, which you might or might not have had before at the beginning of 2020, for example, before you realized this year was cursed. But just think about, like, once the cork is out, like some stuff is going to fountain out of that bottle, but then it's going to be done because the pressure's been released. And so same idea with explosive eruptions. They're violent in a way that if effusive eruptions are not violent and explosive eruptions are very violent. But effusive eruptions last a long time and explosive eruptions are pretty short. We good on that? Okay. So what makes some volcanoes effusive and some volcanoes explosive? Does anyone have any guesses before I switch the slide?
Maybe the amount of pressure that is involved.
Yeah, so the amount of pressure is an extremely important factor, but it's actually just one of three extremely important factors. Anyone want to guess the other two? So the location, so that's a good guess because the location actually controls all three of those variables. So even though the location in and of itself isn't part of the chemistry or physics, it kind of controls the chemistry and the physics. Time, so not necessarily. So volcanoes don't necessarily operate on a regular cycle. Like sometimes a volcano will erupt a whole lot of times in a short span of geologic time and then be silent for thousands of years. It's, you know, they're not cyclical. I mean, they're not like predictable in a cycle. They're sort of monitorable, but we'll talk about how people monitor for eruptive behavior next time as well. But yeah, or let me phrase this in another way. So you need a lot of pressure, but what might control how much pressure can actually be in the volcano? So how
The
hot?
temperature?
Yeah, so temperature is definitely a part of it. But think about, remember what else temperature might have been related to? Like what did we talk about with temperature and igneous rocks last time? Do they all melt at the same temperature?
No, they don't.
Yeah, and so does anyone remember why they don't?
Because on the inside they have more time, and on the outside.
So that has to do with how they cool, which is definitely a temperature question. But in terms of, we're talking about melting. We're going to actually not be talking about cooling a whole lot when we talk about volcanoes. But again, think about what about the structure of those rocks makes them either melt or cool at different temperatures?
The minerals?
Yeah, the shape of the minerals. So the mineral structure actually is a really, really important factor of explosiveness. And so I told you this stuff is basically all how chemistry controls physics. So that's why you'll get to, I'll show you mineral structures again in a second. But yeah, so eruptive style is controlled by what we call the 3 V's of volcanism. So you got basically how much gas is in it. You got volatiles. So how much gas is how much pressure in this case. So while volatiles, when we introduced them last week, we talked about how they help rock melt. But in this case, I mean, once they've reached the surface and they're surrounded by magma or lava, I mean, or once they're in that magma chamber, it's really hot. And so there's not going to be any liquid water in there, for example. It's all going to be water vapor. It's all going to be carbon dioxide, sulfur dioxide. There's going to be a whole lot of gas that is pressing on that lava, that's pressing on that rock. And also definitely the shape of the volcano is going to affect the amount of pressure too. But actually what matters more is the amount of pressure in the lava or magma itself. And so the amount of gas that a magma or lava can hold depends on the shape of the minerals. It depends on whether the mineral structure is such that allows there to be a bunch of gas in it. And so I'll get back to that in a second, but that kind of relates to actually both of these. So volatiles is there a lot of gas in it? And viscosity is how sticky versus fluid it is, which is actually, again, related to that chemical structure. So in order to have a lot of pressure, it has to be viscous. So do you all know what viscosity is in a general, like referring to anything, not just volcanoes? Okay, no. Okay, I'll define that. So viscosity is how well something flows. So something like water is not viscous. Like you pour water and it just flows, like no problem. But if you pour syrup, it's gonna be harder to pour that. Like it's gonna flow more slowly. It's gonna be stickier. It's going to spread out less and be easier to control. It's gonna move slower. Or if you pour then like, let's say you've got your water, your maple syrup, and then like molasses, which is even thicker and stickier. And it's going to pour really, really slowly. Like you might have to, you know, again, if we were in a classroom, I might actually show you this, but I'm not about to pour sticky stuff on my desk next to my computer. But basically, it's just how sticky, how fluid, how easily does it flow? How fast does it flow? And that actually relates back to that chemical structure. So, oops. So big boom. I spoiled my joke. But yeah, let's go back. So volume is just how much is it? If you have a big explosion, then you will need a lot of stuff. So if you only have a little bit of magma in there, a little bit of lava in there, you can't have a very big explosion. Like it might go bang and then just be done. But if you have a whole lot of stuff in there, it's going to be a big explosion. But then that viscosity is like, think about our chain silicates, our single tetrahedral silicates versus our structure, like our framework silicates. So if you think about like how pyroxenes and amphiboles have those little chains that can just slip past each other, kind of like fish swimming past each other. But those quartzes, for example, like imagine a bunch of very sticky, complicated shaped balls trying to pass each other. They're going to get stuck. The mineral structure is such that they get stuck. And so viscosity and volatiles kind of go hand in hand because something that's more viscous can actually hold more volatiles because of the shape of the minerals. Again, I'll get back to that in a second. But sometimes you can have room for volatiles and not have a lot of them. So does that make sense? Do these make sense? I guess I can go through some examples. So let's say you have a low viscosity. Then low viscosity means that it's going to flow very easily. It's going to move quickly. But if it is flowing quickly, it's probably not going to build up and get stuck. But also, if it's flowing quickly, that means it has a mineral structure that allows that. And the mineral structure that allows that doesn't have a lot of empty space in it, so it can't hold as much gas. So if you have a low viscosity, low volatile eruption, it's going to be something like Hawaii, where it's just kind of pouring out of the mountain. Regardless, and Hawaii has a high volume. There's a lot of it, which is why it was able to erupt from 1983 to 2018. But you can have a low volume effusive eruption. But now let's say you had a lot of stuff, or even a little bit of stuff, and it's very sticky, and there's a lot of gas trapped in it. So if it's sticky and there's a lot of gas trapped in it, it's going to make the pressure really high, right? Like that gas is going to want to try to get out, but it's going to get stuck. And because it's stuck, that means more and more gas is going to be trying to push on it. And gas is not viscous at all. Gas wants to flow, but if there's really, really sticky rock blocking that gas from flowing, it's just going to keep building up and building up and building up until the pressure is so great that, again, it pops the cork out of the bottle, so to speak. So on a scale of, you know, a little to a lot of all of these, if you have low volume, low viscosity, low volatile, I mean, you can still have a volcano that does that, but it's not going to be, I mean, you still don't want to touch the lava, don't touch the lava, but it's not going to be like a city destroying kind of volcano. But if you have high volume, high viscosity, high volatiles, you're talking about like volcanoes that can cause things to go extinct. Does that make sense? So we're going to be talking about all three of these a lot for the rest of today and on Wednesday. So even if you don't remember them yet, you hopefully will. But yeah, high viscosity, high volatile, high volume, big boom. Okay, volcanoes in that movie don't work like real volcanoes, but he does say boom there. So anyway, yeah, so viscosity comes into this question of more space for volatiles in the molecules. So again, like this stuff, you know, they're little chains. They're going to flow pretty easily, but this is big and chunky. If you remember, these quartz and feldspars, these felsic minerals are light and fluffy. They're like the marshmallow fluff of the rock world. And there's a lot of, like, you can barely pour that stuff. You can't really pour marshmallow fluff, even if it's still liquid. But there's a lot of air in there. There's a lot of stuff trapped in there. And so if you were to like pump a bunch of gas into some marshmallow stuff, you would totally get it to explode. Whereas if you were to like, even if you were to pump a bunch of gas into, say, a thing of maple syrup, I mean, you would make a mess. It would splatter, but it wouldn't explode. But again, it ties into the shape of the molecules, both in terms of how they flow past each other and if there's space for gas in them. Whole lot of space between the silica tetrahedra in these felsic minerals. Not a lot of space at all in the more mafic ones. That makes sense? And we'll keep talking about this a whole lot over the next day and the rest of this week. But like this, that's why I kept saying, like, you want to know the structure of these minerals. I will ask you things about mineral structure and how it affects volcano behavior on this test. So be familiar with this. And if you're confused about it, again, you can ask me now, you can ask me email, you can ask me in office hours. But yeah, this really controls everything. Something as simple as, you know, 5 atoms stuck together in a pyramid literally controls how big an explosion might or might not be. It's kind of mind-blowing, honestly, when you think about like this microscopic scale feature of a rock or a mineral can control like landscape-changing explosions. It's wild. Volcanoes are cool. But yeah, so this is important. And so with that in mind, actually, eruptive style very much also fits onto this chart that we went over last time. So if you remember, a lot of things are correlated in igneous rocks. So felsic is from feldspar and silica, so high feldspar and high quartz. So that's high silica content, low metal content. Low density, which means it has a whole lot of space, which is a place that volatiles can hang out. It melts and cools at pretty low temperatures. And it's actually very explosive because, again, that high silica content and low density mean it's sticky and traps a whole lot of volatiles if the volatiles are there. But going down to the other end of the spectrum with the mafic and supermafic stuff, so these are all those chain or individual tetrahedral silicates. The silica content is lower. It's maybe only 50% silica and 50% metal. It's a lot higher density. It melts and cools at a lot higher temperature. And that, but again, because it's more dense, it's more chain silicates, there's less room for volatiles to hang out, and so the eruptive style is less explosive. So something like Hawaii is an effusive volcano. It's a mafic volcano. All of the volcanoes in Hawaii are effusive mafic volcanoes. They're not going to be very explosive at all. But meanwhile, something like Yellowstone, which is the other end of the spectrum, is going to be, it's an extremely felsic, extremely explosive volcano. And also worth noting is when we're talking about volcanoes, we're going to be talking about these fine textures, these aphanitic rocks, these extrusive rocks. So these things, rhyolite, andesite, basalt, and komatiite, which again doesn't come out of volcanoes anymore because the earth isn't hot enough anymore. But all of these are going to be lava flows, and these corresponding intrusive rocks or phaneritic rocks are going to be in the magma chambers. So if the volcano shuts itself off and that magma chamber cools, you're going to find granite under a volcano that had rhyolite, diorite under a volcano that had andesite, and gabbro under a volcano that had basalt. But all of these things are related. So just be familiar, again, with how silica content and density and temperature and eruptive style and mineral content all relate to each other, because igneous rocks and volcanoes are actually kind of the most systematic. Like as we talk about metamorphic and sedimentary rocks, there are some rules, there are some classifications. But igneous rocks, everything is extremely, extremely systematic because it is completely related to how all of those little tetrahedra stick together. So any questions here? So again, extrusive igneous rocks, they are lava. So when I'm talking about lava, I'm talking about the things that harden into these guys. So your mafic basalt, your intermediate andesite, and your felsic rhyolite. But the way these things erupt as lava flows is going to be different just because of their viscosity. So here are some pictures of eruptions of each of these styles that they're all effusive. These are all low volatiles eruptions. And so in the case of something like basalt, and this is Batarbunga volcano in Iceland, this basalt, you can see it's kind of oozing out of this vent. It's really flowing. It's making rivers. So this is a very hot lava that is, I mean, hot even by lava standards. All lava is hot, but this is like twice as hot as that. This is going to ooze out and form rivers and travel very far from the vent before it cools in some cases. Meanwhile, andesite has more, it's more viscous. So it's still able to flow, but it goes a lot further. So this is, forgetting the name of this volcano right now, it's in Papua New Guinea. And so it's an island, it's a volcanic island. And here you can see the vent at the top of this. And you can see there's this flow coming out the side. But you can see it's like really thick and blobby. So the scale is very different. Like this is, the photographer is probably standing literally right here next to this lava flow, which is a thing you can do. It's very hot, but you can do that. Whereas this is a picture taken from a helicopter because this is a much thicker, bigger blob of stuff coming out of this mountain. And so these are like, I mean, these are like massive hill-sized, not just like rivers. So it still forms a flow, but it's just a much slower, oozier thing because there's some stickier minerals in andesite. And then rhyolite on the far right doesn't even really flow like this. It's so viscous that its effusive eruptions don't really form traditional flows so much as just blobs. So this is a rhyolite flow. It's liquid. This is still liquid. But rather than flowing, it just kind of forms what we call a lava dome because it's so viscous that it's able to just kind of pile up rather than oozing out. The middle picture of Roku's island, is that from Avatar? I guess that's a pretty, or is that a different Roku? I guess he was the fire avatar, right? That makes sense. I still don't get why volcanoes are firebender territory in there because they are Earth. But I digress. But yeah, this is a very classical looking pointy volcano. This one on the right is Mount St. Helens. It erupted again in 2004. Its very famous eruption in 1980, which we'll talk about a lot next time, was an extremely, extremely explosive eruption. It blew a third of itself into smithereens. But that had a lot of volatiles in it. But in 2004, there were not a lot of volatiles. And so you just had this rhyolite kind of lava bending as an earth bending move. Good, good. Is that from Cora? I haven't seen Cora. I guess I should see Cora. Or am I, yeah, it's from Cora, okay. That one's free now, right? I don't know, I should watch it. Okay, so I feel happy about that because that was a thing that was making me angry about. I love the original Avatar, but the fact that like volcanoes were a fire-bending thing and not an earth-bending thing kind of upset me. But anyway, back to effusive eruptions. This is what a rhyolite eruption looks like when there are not a lot of volatiles. It's just so sticky that it piles up. But yeah, all of these are, when these things cool, these are the rocks that you get out of them. Any questions about this? I guess in the interest of class, I will ask that maybe we can talk about Avatar more at the end, but I do have a bunch more slides. But yeah, does this idea, oh no, it's okay. We kind of got there. But any questions about lava flows? So lava flows when there aren't a lot of volatiles, because if there's no gas, then there's nothing to expulse. It just oozes. But if there are a lot of volatiles, the lava chemistry actually matters a lot more in what's going to happen. So, I mean, in all these cases, a flow is a flow. It just goes a different distance and has a different thickness. But as soon as you introduce, are you all right there? Or is that an animal on the keyboard? But yeah, as soon as you introduce gas to the equation, the chemistry of the individual lava, the specifics of the individual volcano makes a really big difference. So in the case of things with low viscosity, and yes, your cat ran through your keyboard. That's what I heard. But yeah, in terms of low viscosity, and yes, there are going to be a lot of videos from now on, you get what's called a lava fountain. So this is Kilauea in Hawaii in, I think, 2016, 2017. But this is just where you have a low viscosity lava. There's not a lot of sticky. And so when you put a lot of gas on it, it just explodes up into the air like this. And so it just kind of, you can see this photographer is pretty close. This would honestly make me a little bit nervous because if some of this stuff splashes out, you get what's called a lava bomb, and you really don't want to get hit by that. But yeah, this is liquid basalt. This is like 12, 1300 degrees Celsius, and it's just fountaining because there's a whole lot of gas. But at the same time, it's kind of staying in one place just because it is high risk, high rewards. Yeah. So there are people who make a living out of getting very close to volcanoes and taking photos, but there are also people who have died from that. If you're really interested in a kind of catastrophic story about people getting too close to investigate, look up the eruption of Galeras volcano. Really frightening, tragic story. And also Unzen is another one, if you want to hear about people getting a little bit too close. But yeah, this is where you have low viscosity and high volatiles. It's just going to bubble and fountain. But in other cases, if you have a whole lot of, if you have something that's more viscous and it actually is able to trap those volatiles, you're going to get something way more dangerous than this. This, again, if you're at a safe distance, you can probably watch this go if you can tolerate the heat. But for something that has andesite or rhyolite, you do not want to be that close to it because it will blow you up. So actual lava, like lava flows, are not actually nearly as fast as movies make you think. So even go back. Even something like this, like a lot of times when you see a movie, they'll show things like this flowing as if it were like a whitewater rapid of lava. No, it's still rock. It is still rock. I mean, you can outrun this. Like I mean, if you're standing, like and even if you are like the slowest runner in the world, this stuff usually channelizes very quickly. It usually forms sort of rivers. And so if you step to the side, it's not going to get you. Like, I mean, it's still a volcano. It's still dangerous, but like a basaltic eruption like this, you can get very close. And I don't know if any of you saw, there was a video on Twitter recently of some dude scooping out lava from a flow with a hammer. That's pretty safe to do if you know what you're doing. And actually, even I have gotten close enough to a flow like this to shove a stick in it in Hawaii. It shot out blue flames and kind of like, shh, it was really cool. But yeah, there's a lot of, this kind of lava flow is the kind of thing that the media loves to get really wrong. So like, this can't happen. Like, this is a very common thing that happens where like, you fall in the lava, and I think that was it for that clip. Like you see, it's this roiling lava lake, but he just splashes in and he makes a splash and dies. That is not how that works. So let's see, does he die again? Oh no, that's where the bad guy comes out. But like, so in reality, like, see how these boxes are in there? Like, they're not sinking. And actually, you would be able, if you could withstand the heat, if you actually had like heat-proof armor, for example, you could walk across this because it's still rock. Even basalt, even the least viscous of lava is still rock. It is still very dense. It is still so much more dense than you are. You are never going to splash into lava like that. Again, if you had magical heat-proof armor, you could literally walk across that and not sink. And in fact, you could try without the heat-proof armor, but you would catch on fire. So the issue with lava is not that it's going to surround and consume you. There are no heat-resistant potions in real volcanology, unfortunately. No matter how many fireproof lizards you give to the guy at the Southern Mine, you are not going to actually get a heat resistance potion. But again, like the whole like sinking and falling into lava is one of the most common tropes in the book, and it doesn't happen. It's still rock. Like, again, with that basalt thing that I shoved a stick into, like, it wasn't like just a scoop. Like, I had to stab it, even though it was liquid, white hot lava. It's still rock. This will kill you by burning you, but it will not kill you by you sinking into it. So every movie that does that is wrong, all of them. Any questions about that? Moving on. Okay. So we've talked a lot about lava. And by definition, again, you can't have a volcano if it isn't releasing lava. But lava is not the only thing that comes out of volcanoes. It is far from the only hazard of volcanoes. That and heat. So other than lava and other than heat, what are some other things that volcanoes can do to, so gas. Yes, gas is a very big problem, a big one. What else do you think? Ash, yes. Yeah, gas and ash are definitely kind of the big ones, but they can sometimes, oh, okay, so that is the disease where you get volcanic glass in your lungs and it clogs your lungs, right? The thing that Nathan has put in the chat, and I am not going to try to pronounce that. Pneumo lung, ultramicroscopic, tiny silico, again, silicate glass, volcanosis coming from a volcano. So yeah, that's a big problem with volcanic ash. Bad news. I'm impressed that you can spell that immediately. But yeah, ash and gas, well, there's a fun slip of the tongue, are things that spew out of volcanoes. Copy and paste, that's fair. But yeah, there's a lot of other things. So we're gonna talk about those, some ways they combine, and some other stuff that you might not even think of. But yeah, gas, basically that's just volatiles. So for all that we just talked about volatiles that are trapped in lava, I mean, sometimes they're not. Sometimes if you just have a crack or a vent or a place where there's just a lot of gas that is not caught up in the chemical structure of the rock or not trapped behind like a plug, of sticky stuff, then it's just going to spew out into the air. And so the same stuff that tends to be the volatiles that propel stuff forward. So yeah, water vapor, sure. That one's not poisonous. But carbon dioxide definitely can kill you. Sulfur dioxide definitely can kill you. These things are bad news. And the worst part is sometimes you can't even smell them. Like sometimes the sulfur gas will smell like eggs and farts all at once. But sometimes it doesn't smell like anything and you don't notice it until you're choking. And so this is in Hawaii. And this was actually a hike that I tried to go on. And couldn't because there was too much stuff and I had to turn around because I couldn't breathe. This stuff, like even if the volcano is not exploding, even if there's no obvious lava, this is the kind of thing that if a cloud of volcanic gas rolls through your town, it can kill a bunch of people. And there have been issues with that. Like there were some eruptions in the early 20th century in the Caribbean where a lot of people died just from waves of gas. But it's worth noting that a volcano that's still releasing gas, even if it's not actively spewing lava, is still erupting. So this is Kilauea. Actually, I took this picture in 2009. And this is a gas plume. So this is the summit crater of Kilauea. This is where they say the goddess of volcanoes, Pele, lives in this crater. So there is like a pool of lava down below the visible surface here, but there's so much gas coming out of it that this is still considered an eruption, even though you don't see any fire. But yeah, volcanic gas can be pretty nasty stuff. And so they definitely, in Hawaii, monitor the direction of plumes like this. They also have a thing they call VOG, which is like volcanic fog, which is this stuff mixed with just regular atmospheric moisture, real nasty. I imagine it's probably a little bit related to the air quality we've been having now with the fires, even though it's different stuff. But does this make sense? Any questions about gas? So ash was another thing a lot of you mentioned. And so ash is tiny fragments of minerals, rocks, and glass that are blasted in the air from an explosive eruptions. So it's actually not true ash in the sense of being burned up material. So like the real true definition of ash is like what happens from fires, where you have organic material, where you have hydrocarbons that are burned, and after going through this burning reaction, you have ash. So volcanic ash really is just tiny, tiny chunks of ultra microscopic silico stuff. But it gets blasted into the air, usually in a big explosion. And so it's light enough that it can get blasted up, but then it's also still heavy enough that eventually it falls back down. And so this is a photo from the Philippines in 1991, and this is a color photo. This is not a black and white photograph. So this is from the eruption of Mount Pinatubo, which was a massively explosive, really big, like one of the worst disasters, volcanic disasters recorded, and certainly one of the worst, if not the worst, to hit the Philippines. But yeah, this is just gray because of ash. You can sort of see there's like a little bit of green maybe, but yeah, this is a color photo. This is sort of the effect of this. And you might also notice that some of these buildings have collapsed. Yeah, it's really scary. And so these buildings didn't collapse from an eruption itself. They collapsed under the weight of this ash. Like also, if you look at some of these trees, they're all kind of slumped to the ground. Basically, these particles, even though they're individually tiny, are still in mass heavy enough to cause trees to fall over or to collapse poorly built buildings. This stuff is really bad. Even aside from the issue, like Nathan said, of if you get it in your lungs, it can super screw you up. This is also the kind of thing that if it gets into like the engine of an airplane, for example, it can just stop that engine. And so that's why, again, I think I mentioned the 2010 eruption of Eyjafjallajökull in Iceland, where all flights to and from Europe were grounded for over a week because there was so much ash in the air that they were worried about it like screwing up plane engines. And that also happened with the eruption of Mount Redoubt in Alaska a couple years ago. And there was a volcano in Indonesia called Galunggung, which is super fun to say because Gunung Galunggung, Gunung is a volcano in Indonesian, that they actually did have to do some emergency plane landings because of volcanic ash. So this is nasty. This is like, imagine breathing in sharp sand or dumping sharp sand into an engine or just covering your buildings in it. This is bad stuff. And so, but that's not all. So ash can also affect climate. Both ash and gas can block the sun. Basically, if this stuff gets ejected high enough into the atmosphere, it can block the sun. And so you get weird red and orange skies, and you actually get temperatures that are lower, because if there's a thick enough amount of this in the air, it blocks the sun. And if the sun's rays can't hit the surface, in addition to the sky being an awful color, it also makes things colder. And in the case of really big eruptions, so Pinatubo did this a little bit. Krakatoa in the 1880s, which is a very famous eruption, they do things called volcanic winter, where there's so much stuff in the atmosphere that the winter is even colder than it should be, or you get colder than usual temperatures even in the summer, just because the ash is blocking the sun. And so if this lasts long enough, it can lead to poor growing seasons. It can lead to herbivores dying. It can lead to famines. Like a lot of sort of historical famines can actually be linked to volcanic eruptions because of this effect. A lot of mass extinctions can actually be where a lot of different species die at once. Not the dinosaurs, that was a meteor, but actually that was a similar idea of just a bunch of stuff getting blasted into the atmosphere and blocking the sun. So this is really bad. This can affect the climate in addition to, and this can affect the entire world, not just the place that had the eruption. And so if this is sounding a little bit familiar, it's because the fire smoke in the past few weeks actually basically did the same thing. So even though there were no volcanoes involved, there are no volcanoes in San Francisco, there are no volcanoes in LA, but it was the same idea of where all of this just nasty fire ash and smoke and stuff got launched into the atmosphere and formed a blanket such that it was refracting the light in a way and making things orange, and also reducing the temperature. So did you all notice that week when the air was really, really awful and the sky was kind of green and the sun was orange, that the weather forecast said it was supposed to be like 105, but it wasn't? Anyone notice that? Yeah, so that's what was going on. It was very much the same idea, except it was from wildfires rather than from volcanoes. So it's scary stuff. Ash and gas are bad news. But what's interesting is, like, I mean, this is definitely like spooky as heck. Like, this is some real like post-apocalyptic scary business. And it's not just us thinking this in our cursed year of 2020, but there's actually a lot of historic precedent of people doing spooky stuff related to volcanoes. So Edvard Munch's The Scream was painted in the 1880s after the eruption of Krakatoa, and so much stuff got launched into the atmosphere that even though Krakatoa is in Indonesia, people in Denmark were seeing the sky turn red and scary and making people feel like they were losing it. Or going back even further, in the 1814, there was an eruption, or 1815, of Tambora, which is another very large volcano in Indonesia. And that did the same thing, and it made the air red, and it made the winter extremely cold. Sometimes people call that the year without a summer, because there was so much volcanic ash from this very large eruption that it blocked the sun and made things cold and made everyone gloomy and depressed. And Mary Shelley, alone in her house, was like, man, this is depressing. I'm going to write about monsters. So Frankenstein was written during a volcanic winter. So even though this stuff can cause a lot of problems, just because it is so spooky, it's really good we're doing this in October. It gets spooky. But this is volcanoes. You know, they can do some really wild things. So any questions about gas or ash or the combination thereof, or how it screws up the sky and the weather? So because we're not quite done with gas and ash. So when you have them one by one, it's pretty bad. But sometimes if it's really hot and really explosive, they can do something even scarier. They can do something called a pyroclastic flow. And so this is Mount Merapi in Indonesia. And so what this is see how it's this cloud like flowing across the mountain? So this is basically when the ash and gas get hot enough that they start convecting. So remember how when we talked about convection in the mantle, about how hot stuff rises and it sort of flows around and then it gets cold enough that it sinks and then it's closer to the heat source and it rises again? Basically, that's what's going on here inside this cloud of ash and gas. It's just so hot that it starts propelling itself. It actually develops its own convection and therefore its own forward momentum. And so that's why you'll see these things moving laterally. They'll be flowing down. Sometimes they make dust devils. So this is like a volcanic tornado. At night, they're really spectacular looking. So in French, they're known as, I'm going to pronounce this wrong, but nuées ardentes, so glowing clouds, nuées. Someone who speaks French should do that and not me. But yeah, these are basically superheated flowing clouds of self-propelling ash and gas. And these things can go at 450 miles per hour. So yeah, the reason it didn't look that fast in this video is partly just the distance. So this is from pretty far away. This is from in a helicopter. And so the sense of scale here is really tough. But and they don't all necessarily go this fast. But yeah, these things can go at absolutely 450 miles an hour. And so, and they're big. Like this is, taking up the entire side of this mountain. This will kill you. This isn't something like a lava flow that you can outrun and step aside from. If one of these is coming at you, you need to GTFO ASAP. This will incinerate you and fill your lungs with stuff and bury you in ash before you can even run away. So if you've heard of Pompeii, if you've heard of Herculaneum, those ancient Roman cities that got obliterated by the eruption of Mount Vesuvius in 79 AD, that was pyroclastic flow. The gas didn't help, but it wasn't a lava flow. It wasn't the explosion itself. It was one of those superheated clouds basically pouring over the town and just covering everyone immediately. And so here you have people that, these are, yeah, I'm sorry, here's a picture of dead people, but they're completely encased in stone. This is because they were just sleeping and then this pyroclastic flow came and, you can see this guy was kind of trying to get up and get out of the way, but it just completely, just encased them in molten rock immediately. And so a lot of the stuff in Pompeii, also the fact that these people are exposed is because they had to be dug out from an even thicker layer of this stuff. These are scary. I think this is the scariest thing that can come out of a volcano. And so again, pyro, heat, clastic, little particles. But yeah, these are terrifying. And so these only happen in intermediate or felsic volcanoes. You need to have a pretty sticky lava for this to happen because it requires a really big explosion to make things hot enough and pressurized enough to start convecting. So you're never going to get something like this in a place like Hawaii, or probably not in a place like Iceland, but you will in places in like subduction zone volcanoes. And we'll talk more about why next time. But any questions about these really horrifying things, pyroclastic flows? I guess with these folks, at least it was quick. It is pretty quick. Yeah, the Mount St. Helens eruption, I think very nearly all of the deaths in the 1980 Mount St. Helens eruption were also from a pyroclastic flow. But yeah, so those are bad. But there are some other things that volcanoes can do that don't even necessarily require the volcano to actually be erupting. Because sometimes volcanoes, they're hot. By definition, they're hot. Like especially if the magma chamber is pretty close to the surface, or if there is lava in the conduit, but it isn't actually coming out. It can be hot enough to make the surface warm and to do things like, say, melting snow or glaciers. And so in that case, you get something called a Jokulaub. which is an Icelandic word. And this is Eyjafjallajökull, again, in Iceland in 2010. And so in this case, the volcano was erupting. But basically what happened is if the volcano is under a glacier or a snowcap, so here you can see the glacier, and all of this mud and stuff pouring out from under the glacier. That's because the volcanic heat started melting the ice. And then all of that water started flowing out from under the glacier and usually probably mixed with volcanic gunk. And it just causes this flood. And again, the volcano doesn't have to be erupting for this to happen. It was in this case, but just so long as it gets hot enough that it melts a lot of ice, you can have a volcano that is not actually erupting at all and still produce these rivers of ice and molten, well, not molten, I guess water is molten ice, I guess, of water and volcanic stuff pouring out from under the glacier. And so the reason this is an Icelandic word is because Iceland is the place where you have most volcanoes that are under glaciers. Almost every volcano in Iceland is actually under a glacier. So this happens a lot. And so yes, water kind of is ice lava. I'm not gonna ever ask you to spell this word, but I would like you, if you see this word, to know what it means. So you don't have to be able to pronounce Jökull. Jökull is Icelandic for glacier, by the way, but you don't have to be able to pronounce this, but I would like you to recognize it. You don't have to spell this, but I'd like you to know what it is. And there's also a similar, well, actually, any question about those? So there's a similar thing that can happen even without ice, and that's called a lahar, and that's an Indonesian word because this is extremely common there. And so this is it's a similar idea, but just without the glacier. So it's caused by when you suddenly get a lot of water mixing with volcanic debris. So sometimes it's caused by snow melt, like if it snowed in the winter and then it gets warm and the snow melts, or sometimes it's just caused by heavy rain. In Indonesia, it's usually heavy rain, but in different places, this happens. So this happens in lots of places, not just Indonesia. It's just the most common there, which is why this is an Indonesian word. But basically what happens is the same idea is you get a bunch of liquid at the top of a big pointy mountain that has a bunch of like ash and debris and gunk lying around, and that's gonna turn into mud and pour down the sides of the mountain. And in this case, you don't even need the ground to be hot. So while in a Jökull, it still needs to be hot enough for the ice to melt. In a lahar, this can just be purely related to weather. Just you get one, like, you know, Indonesia gets a lot of tropical storms. You get one tropical storm, and in addition to all of the hurricane stuff, you're suddenly dealing with nasty mud flows pouring down the volcanoes from all the rain. So this is a volcanic hazard. Even if a volcano hasn't erupted in hundreds of years, this can still happen. Although it's more common in cases, oh, wait, this isn't playing. I just realized it's not playing. So even in cases where the volcano is not actually erupting and hasn't for a long time, this can happen. But it is more common in volcanoes that are more active, both because they're pointier, and also because the more stuff that's coming out of them, the more just loose debris is around to mix with the water. So, you know, this looks just like a flood. And honestly, from a way that it affects the landscape, it basically is a flood. But the reason we call it a volcanic hazard is this wouldn't happen without all the loose volcanic debris. And so that guy probably a little bit closer than he should be. But yeah, this is what happens when you mix a lot of water with volcanic debris. So this is also Mount Merapi, which is a very active volcano, but I don't think it was actually erupting here. But yeah. In the interest of time, I'm going to pause that video because I've got like one more slide. But these videos will also be up when I upload the PowerPoint to Canvas after class on Wednesday, so you can watch all of these again. But any questions about lahars? Once again, you don't need to spell this or pronounce it. I just want you to be able to recognize this word and know what it is. Although this is a much easier to say word than Jökull. Um, but yeah, so there are a lot of hazards associated with volcanoes. In the grand scheme of things, even though volcanoes are kind of defined by lava, lava is not the thing you have to worry about the most, even though it is the most photogenic. But yeah, so where we're going to end things today is getting back to our thoughts about the three V's. Because even though all of these things can come out of volcanoes, it ultimately, with the exception of Yokulalps and lahars, still does tie back to how explosive the eruption is. And so, as we said, viscosity is controlled by mineral structure. Volatile content is partly controlled by viscosity, like how much gas can that hold, and partly controlled by what's there. Like if there isn't any gas there, no matter how much space there is in the mineral structure, it's not going to have gas in it. So volatile content, there has to be volatiles and it has to be able to be held in the rock. Volume is controlled by how much rock has melted. Pretty straightforward. But all three of those things tie back to what several of you were saying at the beginning of the class when I asked what controls this, about the place. And so in this case, when I mean the place, I mean the tectonic setting. What kind of plates are melting and how and where did they melt? Really controls a lot. So like if you have an ocean versus ocean subduction zone, you're gonna have mafic or intermediate rocks. So it's gonna be, it can still be pretty explosive, but it can be effusive. High volatiles because you're dragging water down there. Continental versus ocean subduction, meanwhile, you've got a lot more felsic stuff in the continental plate, which means even though this oceanic plate is still mafic, it's dragging down a lot of volatiles and you've got much stickier rock. So this is going to be intermediate or felsic and have the potential to have a really big boom. A continental rift is in a continent. Continents are felsic, so it's pretty sticky. But as that rift spreads, it's going to get more mafic. A hotspot super depends on whether the hotspot is under the ocean plate or under the continental plate. It could be a really, really mafic, really, really effusive thing like Hawaii, or it can be a really, really felsic, really, really explosive thing like Yellowstone. And then lastly, at your mid-ocean ridge, that's mafic. That's just a straight tap into the mantle. So that's going to be pretty mafic or ultra mafic. And even though it's in the water, and we talked about water vapor being a volatile, because the water there isn't a vapor, it's just water. These are actually usually pretty low volatiles. And so you're going to get different kinds of volcanoes at all of these places. And that's where I'm going to leave off from now. So I'm going to start with this slide again on Wednesday, and then we're going to go through the different kinds of volcanoes that form in different places and the different ways they behave as controlled by the three V's. So with that, I'm done. You're welcome to take off, or if you want to stick around and ask more questions, I will hang out for a little while. So if not, again, don't forget, quick quiz will be up. You're welcome to come to office hours tomorrow. See you Wednesday.
Thank you, Professor.
Thank you. Yeah, you have a good one too. Chris, Crystal, Hassan, and Jonathan, are you hanging out for questions or writing stuff down? Okay. All right. I'm going to end the lecture. So if you do have questions, just feel free to either email them to me or come to office hours or just ask next time. So have a good one.